All right, this lesson is on misleading graphs. A lot of this lesson is just going to be kind of hearing and reading. You're welcome to pause at any time to read on your own. So, statistics is one of the most applicable branches of math for our lives because statistics are presented to you pretty constantly. Having a working knowledge of statistics will help you to be more informed in our modern world. Unfortunately, sometimes our data can be misleading or be biased. So, misleading data are ways that professionals out there can make data that says something that they want you to think. Paying attention to how data is presented is crucial to understanding the information that is presented to you. There's also biases. Biases are prejudicial tendency towards or against a person or idea. This topic will also probably be covered in your social studies classes when you read or discuss stats. It's important to understand the bias of the source. You can ask yourself, what point are they trying to make? What is their politics? What might be they trying to hide? So example 1, to the right is a supposed pie chart. So it's a snapshot of a TV showing you the 2012 presidential run, and it shows you the source, who's the TV show, and then if we look at the pie chart, we're trying to figure out what might be an issue here. So think about Venn diagrams from probabilities. Sometimes we get people who fall within more than one group, so they could overlap. So if we think of set A and set B, and then we have people who fall in both of those categories. To describe these, we use contingency tables and Venn diagrams. Because that will show you the difference when they overlap. A pie chart is typically used to show parts of wholes where the slice represents a distinct category, and it must always add up to 100%. So pie charts must add up to 100%, and they want it to be a distinct category. The issue arises when the categories are not mutually exclusive, meaning that people can fall into more than one category, and there's overlaps within those groups. If we try to represent this kind of data in a pie chart, that total no longer adds to 100%. So if we look at this pie chart here, notice that 70% and 63% and 60% is more than 100. So this is considered a misleading pie chart. If you have two categories such as people who like chocolate, so here's our chocolate people, and those who like vanilla, using a pie chart might be misleading because they might like both. So you're double counting those people. So that'll again add up to more than 100%. So we would not want to use a pie chart for this scenario. All right, example 2. We have an interesting case where baby seems to be getting much bigger very quickly. Why is this graph misleading? So baby Gemma has a high temperature. So here's the temperature. And then this is the time. And we notice that the temperature is going down. Okay, why is this line graph misleading? Number 1, scale issues. One common reason for a misleading graph is sometimes the x-axis or the y-axis is not scaled appropriately. For example, if the vertical axis, the temperature, has a very narrow range, making small changes could make the temperature look more dramatic than it really is. Alternatively, if time intervals on the horizontal axes are too wide or too narrow, it might distort the perception of how quickly the temperature is changing. So again, the temperature range is only from 38 to 40. So a pretty narrow scale. And alternatively, the horizontal axes could be too wide. So here's noon, and then this is 3 o'clock, and then all of a sudden it goes to 3:30. They're not equally scaled here. So again, we have noon, and then 3 p.m., and then all of a sudden it just goes to a half an hour more. So these are not equal. So we don't want to have these equal timed. Data points. Another reason for the graph could be misleading is the points may be too far apart in time. For instance, if the temperature is only recorded at a large interval, like every hour or every few hours, it might make the temperature drop suddenly very quickly over time, where in reality it's just slowly decreasing. Unclear starting or ending points. Sometimes the graph might focus on smaller segments of time, making it appear that the temperature has dropped quickly. If we don't know the exact time of the temperature to begin to fall, it could also look, so here's that time at noon, and then again at 3 o'clock, and then a half an hour later. Where does the temperature reduce the most quickly? To determine this, we look at the slopes. So here's a pretty drastic slope change. So that looks like the greatest change in slope, but the time allotment was 3 hours. And then only a half an hour later, the slope can be very confusing. So in summary, a misleading line graph may exaggerate the speed of temperature and reducing the scale or time intervals is not helpful. All right, example 3. At first glance, it appears the data shows terrible unemployment numbers. So here's our unemployment rate under President Obama in 2011. Look carefully at the percentages. What might you expect them to start? So we have January of 2011, and the employment rate was about 9%. Then February, 8.9, March, 8.88, etc. And we want to figure out why would this maybe be misleading. Notice on the side percentage go up by 5%. So 8%, 8.5, 9, 9.5, and 10. And then on the line graph, they go up by 0.1%. This causes line to move much more. If the line is moved by the same percentage, 0.5%, it would look relatively flat. Typically, unemployment percentages for most countries or regions hover in a certain range. For instance, In many developing countries, unemployment ranges range from 4 to 10%, depending on the country and the economy. If the graph shows high unemployment rates, that would seem extreme at first glance, example 20% or more, it could make it look misleading or isn't clear. Given that the percentages on the side increase 5%, but the line itself increases by only 0.1%, this suggests that the scale on the graph isn't evenly applied. The scaling issue could make small changes in employment appear much more dramatic, and leading us to believe unemployment is much worse than it really is. The side percentages increase from 5% or 0.5% on the x-axis again. So on the vertical axis, so that's this axis here, where the actual increase is 5% along here. The line graph increments could be flatter, so I'm just showing you that scaling again. Another thing is comparing October to November. So here's October, 9%. And then okay, it's hard to read, 9.5%. It might seem a little bit significant. Alrighty, let's move down to, again, I talked about the scaling issues. All right, last thing to finish up is those outliers. Another way that data can be impacted is having an outlier in your data set. So if we imagine here's our data points and we want to find the mean, we would add up 5 plus 7 plus 2, 9, 4, 4, 18, and 1, and divide it by 8, we get 6.25. Now, if we exclude that outlier, so we have 5 plus 7 plus 2, 9, 4, 4, and 1 divided by 7, we get 4.57. So quite a difference of having that 18 in there as an outlier and how it affects the mean. Mean is the measure of the central tendency that typically impacts the most by including an outlier. So sometimes statisticians will try to leave that outlier in to make it look misleading. So here's some summaries of way graphs can be misleading. Sometimes the vertical axis, so here's your vertical axis, could be scaled incorrectly by being too big or too small. The vertical axis might skip numbers, so it might jump all the way. It might not start at 0, start at 5, and then just go to 8, and they really should include these numbers down here. A graph is not properly labeled, so it might be missing an x-axis, a y-axis label, or a title. Some of the data might be left out. Scale might not start at 0, like we showed here. Scale may maybe have very small units to make the graph look very big, or missing labels in the graph. Incorrect scale placed on the graph. We talked about the pie charts. Remember, a pie chart, it needs to add always to 100%. Oversized volumes of objects that are too big or too small on a vertical axis. The size of images used in a graph might be not categorized correctly in the same shape or size.